Hi everyone. Hope your home-based learning has been working well for you so far. Now, recently it's been announced that it is mandatory for everyone to wear a mask whenever they leave their house. And this is largely in part due to some studies which have shown that many tiny water droplets can linger in the air. Water droplets that are produced when someone talks or when someone coughs or sneezes. And I thought it would be interesting to do a video showing how we can calculate how long one of these droplets can stay. Okay, I believe it should be quite common sense for you. You will be able to intuitively see that a large water droplet will drop to the floor very quickly, but whereas if you have tiny water droplets such as those in the aerosol spray, those will fall much more slowly. Just to illustrate this fact, have a look here. This is a side-by-side slow-mo video comparison of tiny droplets in an aerosol versus a large droplet from a dropper. Now, if you had guessed that this had something to do with air resistance, you would be absolutely correct. Okay. Now, if you look at the screen, for a falling object, it is moving downwards, right? So our air resistance is going to resist the motion. It's going to be pointing upwards. It's an upwards force on the droplet. And as the droplet speeds up towards the Earth due to the Earth's gravity, the velocity is going to increase, and so the resistance force that it experiences from the air also increases. Now, at some point in time, this air resistance is going to be equal in size to the weight. Okay, when this happens, then there's not going to be any net force. The net force on the droplet is going to be zero. Okay, and when this happens, then there is nothing that will cause the object or the water droplet to speed up anymore. Okay, it will continue to fall at a constant velocity, and this is what is known as terminal velocity. So how does this relate to our water droplet problem, right? You can see that the smaller the water droplet is, the slower it falls, right? So that means the slower the terminal velocity is going to be. Now, is there any way that we can prove this or calculate this from a physics standpoint? Okay, in order to do that, we have to look at this equation over here called Stokes' law. Now, Stokes' law is an equation that you will likely only see if you do engineering in the university. And what it does is it allows us to calculate for a spherical object that is moving at a relatively low speed through the air. It allows us to calculate the air resistance. Okay, and so from this equation, we can see that air resistance is going to depend on certain things. Like what we mentioned earlier, it depends on the velocity of the object. It also depends on the radius of the object, in this case, the radius of the water droplets. And it also depends on this thing called the viscosity of the medium, which is the air in this case. Okay, so viscosity is a measure of how easily something can flow. So for example, honey, honey is like kind of thick, and if you try to pour it, it actually flows very slowly. Okay, so that is an example of a fluid with high viscosity. So you can imagine for air, right, air is going to flow quite quickly, quite easily. And so the viscosity for air at 25 degrees Celsius temperature is quite low at 1.837 times 10 to the minus 5. Okay, so this equation is what allows us to calculate the force of air resistance. And if we put this back up here in this equation, then essentially we will come up to something like this. Now, recall that our point here, right, is to try to calculate based on the radius, the size of the droplet, the speed at which it will fall, the terminal velocity at which it will fall. Okay, now if you recall, terminal velocity happens when the air resistance is equal to the weight. Okay, now weight is given by the mass times the gravitational field strength, right? The mass of the droplet. But the mass of the droplet is not what we are working with. We are trying to work with the size of the droplet. Okay, so we have to do some conversion here. And over here in my working, you can see that the conversion required is that of density. Okay, so for the water droplet, the density of the water droplet is mass over volume. Okay, And since we are assuming that this water droplet is a sphere in shape, then volume can be found by this equation here, 4/3 pi r cubed. Okay, so making m the subject, we can come up with this expression here, which we then substitute into the equation. Okay. Now, long story short, once you finish the substitution and make v the subject, you get this equation that allows us to calculate the terminal velocity of the water droplet. Okay, for the terminal velocity of the water droplet, you can see that it is related to the square of the radius. Now, skipping ahead, I've done some calculations, and the results are what you see here. So I have tried the calculation for different droplet sizes, and we find that for smaller droplet sizes, 0.01 cm and below, the terminal velocity of these droplets is 1 cm per second and below, even up to 0.01 cm per second, which is, as you can imagine, quite slow. So this will kind of match up with what the reports show on water droplets hanging in the air. Okay, now bear in mind that these numbers are based on perfectly still air. And you know, when you're outside or when you're in an aircon room, there is going to be some movement in the air due to people moving around, due to aircon blowing, or you know, there's some wind, and so on and so forth, right? So all these are going to contribute to the droplets hanging around in the air even longer. Okay. Now, some of you may also have realized that this actually explains why clouds can stay in the air as well. Clouds are essentially big gatherings of millions and millions of very tiny water droplets. Okay. And these water droplets, if they are very tiny in size, are going to hang around in the air, right? Just because of some upwards air currents and so on. Okay, but over time, these water droplets, they will coalesce into larger droplets, right? And then they will start to fall. And then that's what we call rain. Okay, so I hope you found this interesting, informative. And please help me to like and subscribe. And if you have any suggestions for other videos that I can do in the future, please add them in the comment section below. Okay? Thank you and stay safe, everyone.